Source-free circuits composed of a resistor, inductor, and capacitor in series can be analyzed using some basic equation conventions. It doesn't matter which order the capacitor, inductor, and resistor are in, they just need to be in series in some way in a loop for it to be a series RLC circuit. There are a couple required conventions. Whatever direction for current you choose, the voltage drop across your capacitor needs to match the sign convention for current and voltage terminals over a capacitor. Current is traveling up through the capacitor, so we have a positive terminal leading into a negative terminal. This is going to be the voltage of our capacitor. If your current looked like this instead, then our voltage terminals for the capacitor would be as follows. Once you have the conventions in place, it's time to determine the equation that you can use to handle a series RLC circuit. In a series RLC circuit, you can instantly determine an equation for I of t, and by instantly I mean sort of instantly. You need to know alpha and omega. Alpha is equal to R over 2L for an RLC circuit. Omega naught equals 1 over the square root of LC for an RLC circuit. And when you solve this circuit for its special differential equation, the roots of the characteristic equation for that differential equation will be negative alpha plus or minus the square root of alpha squared minus omega naught squared. This leads to three possible solutions. If alpha is greater than omega naught, then the term inside this square root will be positive and real, and I of t will take the following form. A1 e to the s1t plus a2 e to the s2t, where s1 and s2 are this s root, but you take the positive or the negative version of the root. If alpha equals omega naught, you get the following form. I of t equals a1 plus a2 times t times e to the negative alpha t. Note that this is because alpha squared minus omega naught squared goes to 0, so you're just left with a negative alpha. So the s's here become alpha, negative alpha, but we needed to add this t term because of what we did when we solved the differential equation. If alpha is less than omega naught, then alpha squared minus omega naught squared will be a negative number. So the square root of that negative number will be imaginary. When you have an imaginary term in an exponential expression, what you result in is a cosine and sine terms using Euler's formula. And we do some finagling to that to get the following format. E to the negative alpha t, the real scaling factor, times b1 cosine omega dt plus b2 sine omega dt, where omega d is the square root of omega squared minus alpha squared. Note that because alpha is less than omega, this will actually be a positive term, so omega d will be a positive frequency. So what we'll temporarily call step 1 is to determine the form of I of t based on alpha and omega naught, and write that down. There are other steps, and you can technically do them in any order you wish, but I've started by determining the form of I of t. However, in order to finish solving this equation, we need to know what the constants a1 and a2, or in this case b1 and b2, are for our various forms of I of t. To do this, we need initial conditions. Initial condition 1, the current at time equals 0. Initial condition 2, the derivative of the current at time equals 0. If you have the initial current in the inductor, I0, and the initial voltage in the capacitor given the correct terminals, V0, it is pretty easy to determine the derivative of I at 0. All we need to do is determine the voltage across the inductor because VL equals L di dt as long as we use these sign conventions for voltage. Current leads from a positive to a negative terminal across an inductor. If we give the inductor, the capacitor, and the resistor the same passive sign convention, positive to negative, positive to negative, positive to negative, we can set up KVL very simply as the sum of all of the voltage drops is equal to 0. Note that if we're following the typical KVL convention that I've been using in my videos, we'd be hitting a drop, and then another drop, and then another drop. So we'd write negative, 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 but all those negatives would cancel out. So I just wrote them as a sum of voltage drops equals 0. Now, at time equals 0, the voltage across the inductor is L di dt at 0. The voltage across the capacitor is simply V0, and the voltage across the resistor is I0 times R, and all this is equal to 0. We can solve for di dt by subtracting V0 and I0 R to the right side of the equation and dividing by L. Observe that this basically says, as long as this voltage is positive and this current is positive, that the change in current is negative. This should make sense because in a system with a resistor, the energy represented by the current should be slowly getting dissipated by the resistor in the form of heat. So the current should be decreasing because the only thing providing the current is starting to lose its energy. Anyway, once we have the initial current and the initial change in current, we can plug I0 into this equation, supposing that we were using this equation, and that would be a number, a number, a number. All of these would be constant. T would equal 0, so we'd just be left with a number equals A1 plus A2. Then we can take the derivative of this entire equation, which would give us A1 S1 e to the S1t plus A2 S2 e to the S2t. Plug in t equals 0, and you lose both these terms as 1, and plug in di dt at 0, and you're left with a number equals A1 S1 plus A2 S2. Basically, you are plugging in the two initial conditions in order to solve for the two constants. We're going to do an example to demonstrate how this works, but let's clarify that step 2 is to determine the initial conditions of the circuit, and step 3 use the form of the equation for the circuit and the initial conditions of the circuit to determine the constants for the form of the circuit.